Welcome to Lecture 4.1, Boundary Value Problems. Let's begin with a few words for how a boundary value problem differs from something that you're probably a lot more familiar with, namely an initial value problem. So suppose y is a function of time, so we'll write y of t. Then the following is an example of an initial value problem, or an IVP. I'm not going to give you a full complete definition, I'll just give you two examples. You can compare and contrast and understand what the important differences and features of each are. So for an IVP, we need an ODE, for example, y double prime plus 2y prime plus 2y equals 0. Let's just suppose y is equal to position as a function of time. It doesn't have to be, but it's just easier to describe in English if it is. Then what makes this an initial value problem is that for each derivative, we have to specify an initial condition. So, for example, in this problem, y of 0 equals 1 and y prime of 0 equals 0. So this first one, think of it as saying the initial position is 1 and the initial velocity is 0. In contrast, boundary value problems usually arise more naturally when we have ODEs involving functions of position. So here we use the variable x. Now we don't have to do this. We could have an initial value problem with a variable x and a boundary value problem with a variable t, but just physically, these are the ones that typically arise, and we'll see why shortly. So let's let y be a function of position, and this is an example of a boundary value problem, or a BVP. So let's use the same ODE, but now let's specify the value of the function at two different places, 0 and pi, for example. So here, think of y as maybe the temperature. And so if we have, maybe we have a rod here, and we're saying that the left endpoint, the temperature, so this is position x equals 0, and this is position x equals pi. And maybe x is in radians, so this is something that's maybe a semicircle that's going around 180 degrees. So again, an initial value problem, we specify all of the derivative, well, this is a second order, but for an nth order, we have to specify the 0 up to n minus 1th derivatives, whatever value they take, at t equals 0. That's the key. It doesn't have to be 0, but all of the inputs have to be the same. For a boundary value problem, we don't have to specify the values. We could specify the derivatives, but the key here is we have to do it. It has to really be a second order. That's not true. It doesn't have to be a second order ODE, but it often is. And if it is, we have to specify these values at different inputs because physically they represent maybe a one-dimensional region, and 0 and pi are the actual physical boundaries of that region. The theory, namely the existence and uniqueness of solutions of initial value problems, is well understood, and you know some of it. So you know that if you have a linear homogeneous ODE of order n, then the general solution is a vector space of dimension n. And moreover, if you have n initial conditions like this, then you get a unique solution, so one and only one. So for example, we're guaranteed that for this problem, this IVP here, there will be a unique solution. In contrast, boundary value problems are more complicated. So for this one, we don't know if there's going to be a unique solution, or no solutions, or many, or infinitely many, or something else. Okay, so it's not too important, but just for practice, let's solve both of these because we can. So if we solve this ODE, you assume there's a solution of the form y of t equals e to the kt, and you plug this back in, and you get k squared plus 2k plus k, not plus k, plus 2 equals 0. So we get that k equals negative 2 plus or minus b squared, so that's 4 minus 4ac, that's 8 over 2, and that's 1 plus or minus I. So that means that we have a solution of the form, let's see, so we have y1 of t equals e to the 1 plus I t, and y2 of t equals e to the 1 minus I of t. Now, of course, we don't like to write things with complex exponentials, unless we're computing a complex Fourier series, of course. So instead, we can write this general solution y of t as a. Do you remember how to do this? So you write this as, oops, this is good review, e to the t times e to the it, then you use Euler's formula, and with a little bit of simplification, you get a e to the minus t cosine of t plus b e to the minus t sine of t. If you don't remember how to do this, if you don't remember how to do this, please consult my basic ODEs course. I have a whole lecture on stuff like this. Okay, so let's use the initial conditions now. So if we plug in 0, y of 0, we get a, and that has to equal, let's see, do we get a? Yeah, so we get a times 1 plus 0, so a, and that equals 1. So we know what a is. So now let's use the next initial condition. So the next one says that y prime of t, let's take the derivative first. So first of all, I can let a be equal to 1, so I get negative e to the negative t times cosine of t minus e to the negative t sine of t. That's the product rule. And then plus b e to the negative t cosine of t minus b e to the minus t sine of t. Okay, so let's plug in 0. Maybe this was a harder problem than I intended, but let's see. So let's plug in 0. Y prime of 0 equals, so we get negative 1 here, we get 0 here, we get b times 1 here, and then we get 0 here, so we get that b equals 1. Okay, so we have our general solution. As guaranteed, the solution is going to be, well, we got lucky here. A and b are both 1. So it's e to the negative t cosine of t plus e to the negative t sine of t. So there is our solution to this initial value problem. Let's do this boundary value problem now. So we get the same general solution, but now if we want to use the boundary conditions, y of 0 equals, we plug in 0, we get a, and that equals 0 because we get a times 1 plus 0. So now we know right away that there's no cosine term. So let's do y of pi. Let's plug in pi. And so we don't have to worry about the a term. We just look at the second term. We get b e to the minus pi times sine of pi, and that equals 0. What does that tell us? Well, sine of pi equals 0, so b can be anything. So we actually get infinitely many solutions here. We get y of t equals b e to the negative t sine of, oh, I've been saying t, I should be saying x here. So let me back that up a little bit. Sine of negative e to the negative x sine of x. So that is our general solution to the boundary value problem. So here we have infinitely many solutions. Here we only have one. Let's do 3 more examples. I've picked these 3 because I want to compare and contrast the different possibilities of the solutions to boundary value problems. So for all of these, the ODE has the same general solution. I picked the same ODE. So it's y of x. I'll call it a cosine of x plus b sine of x. I'm using x instead of t because, again, boundary implies position instead of time, and it just makes more sense, or it usually comes up more when there's 2 different points in space, or position, versus points in time. Okay, so this first one, let's plug in 0 and then plug in pi and set them both equal to 0. So y of 0 equals a, which is equal to 0. So that kills off the a term. And now y of pi, the a is already gone. We don't need that, so let's just write b sine of pi equals 0. So this is a lot like the problem that we just did in the previous slide. This doesn't tell us anything. So this tells us that b times 0 equals 0. B can be anything. So the general solution is y of x, or not the general solution, just the set of all solutions, I guess that's really the same thing, is b sine of x. So there are infinitely many solutions. Let's do the second problem. So it's got the same general solution, and now let's plug in these boundary conditions. That's what we usually call them. I'll use blue here. So y of 0 equals, as before, well, I guess for all of these, that tells us that a is equal to 0. So y of 0 is a is 0. So the difference comes when we plug in this case, pi over 2. So if we plug in pi over 2, we get b sine of pi over 2 equals 0. And let's recall what I always have to look at the unit circle to remind myself. Sine of pi over 2, that's the y value right there. So that's equal to 1. And so this tells us that b times 1 equals 0, because again that is equal to 1. So that means that b equals 0. So here we get that y of x equals 0. There's one and only one solution. It's the trivial solution. And finally, for the third example, as before, we get y of 0 equals a, which is 0. But now things are different when we get, say, y of pi equals 1. So y of pi, let's plug pi into here. So y of pi equals b sine of pi. So b times sine of pi, and that equals 1. Now where is sine of pi? That sine of pi is the y value here, and that's equal to 0. So we get that b times 0 equals 1, and so there is no solution. So here there is no solution. So we have three of the same ODE, but now we have three different sets of boundary conditions. One of them gives us infinitely many solutions, one gives us one solution, and one gives us no solutions. And I think it helps if we sketch what these functions look like so we can understand this better. So let me do all three of them here. So the first one says, suppose we have, so when you see this, that says sines and cosines, so which is a sinusoid. Remember, we can always write something like this as a single shifted cosine or sine wave. So here we have, this is pi. So if we sketch, so anything of the form b sine of x is going to work. So for example, there's a function. This is say sine of x. We can have 2 sine of x, 3 sine of x, etc. Any of these, even negative, is going to set. All we need is that we need a sum of sine and cosine waves like this with period 2 pi that go through this point and go through that point. So there's a whole infinite family of them. And for the next one, so here's pi and here's pi over 2. Now, how many of these sine waves? So these are the guys that solve the general solution, and so this family solves this general solution, and the first condition, because that first condition, y of 0 equals 0, that forces this y of 0 equals 0. So we're looking for sine waves, sine or cosine waves. Now they have to be sine waves because of this condition. So they go through 0, and they have to go through pi. There's infinitely many of them. However, if we force them to go through pi over 2, none of these functions here are going to go through pi over 2 except, well, there's one of them. That's the 0 function. So if we require that our functions of this form go through that point and that point, there's only going to be one of them, and that's the 0 function, and that's what we got. That's what we got right here. Let me draw this in blue because I've been using blue for this. And finally, the last one, so this is pi, and again, this is pi over 2. So of all of these functions here that satisfy this ODE with this first boundary condition, how many of them go through the point 1? So this is 1 up here, that point. None of them, because they all go through this point. At pi, they all equal 0. None of them equals 1. So there's not going to be any function here that's going to go through this point and that point that's going to solve this piece. In other words, is going to be of this form. So that's a picture as to why. So this is the graphical or geometric reason for why this is true, and this is the algebraic reason. We'll conclude with a series of 4 examples, which are all very similar to each other, but they're going to come up repeatedly when we study partial differential equations later in this class. So all of these, when we try to solve a PDE, are going to arise as subproblems. And we should solve them now because they fit in the context of this lecture. Okay, so the first one is solve the following boundary value problem. Y double prime equals lambda y, subject to the 2 boundary conditions, y of 0 equals 0, and y of L equals 0. So these are both called Dirichlet boundary conditions because we're specifying the value of the function at the endpoints rather than, say, the derivative or a mixture of the two. So this is the simplest case. So now I haven't told you what lambda is. Lambda could be positive or negative or 0, and we have to handle each of those cases separately. So the way to think about this is think of y as like maybe the temperature of a bar of length L. So this is x equals 0, and this is position x equals L. Maybe the heat can only flow that way, and maybe the temperature is, this says it's fixed to be 0 degrees at 0 and L. So that's a picture as to what this might model, and we'll learn more about this later. Okay, so we need to do 3 cases. Lambda could be 0, or positive, or negative. So do the case where it's 0 first. That's the simplest. So suppose lambda is equal to 0. Then we have y double prime equals 0, and that's a simple ODE, and not really even an ODE. We can just integrate it twice, and we get 2. What function has a property that its second derivative is equal to 0? Well, linear functions. Y of x equals ax plus b. So we have a linear function that if you graph it, at 0 it takes the value 0, and at L it takes the value 0. So it goes through these points, and so it clearly has to be the 0 function. Now if you want to verify this algebraically, you can actually plug these things in. If you plug 0 in here, you get y of 0 equals b, and that is equal to 0. And then if you plug in, so b is 0, if you plug L in to here, then you get y of L equals a times L, and that is equal to 0. That tells us that a is 0, because L is non-zero. L is different from 0. So we get right away that y equals 0. So there are no non-trivial solutions to this boundary value problem if lambda is 0. Okay, case 2. Suppose lambda is positive. Now if lambda is positive, it's going to be easier if I write things as omega squared. So I'll write omega, so omega squared is positive. So this gives us the ODE y double prime equals omega squared y. So this is the equation that we want to solve now. This has general solution, y of x. Well, there are 2 ways we can write this. We can write this using exponentials, which you're probably familiar with, but I also want to get you into the habit of whenever you see a boundary value problem, and you have this ODE, use sinches and coches, the hyperbolic sines and cosines instead. But since those are relatively new to you, I'm going to do this both ways to see how you get the same answer. But because of this, I'm going to go fairly quickly. So this first one, y of x is c1 e to the omega x plus c2 e to the negative omega x. Now let's plug in 0 and L, and let's see what we get. So now if we plug in y of 0, we get c1 plus c2 equals 0. And if we plug in if we plug L into here, so y of L equals c1 e to the omega L plus c2 e to the negative omega L. And omega L is just, this is some positive number. That's all we care about. I should say that L is positive. Okay, so we need to solve this system. And so this first one tells us that, say, C2 equals negative C1. And so if we plug that into here, what we get is C1 e to the omega L minus C1 e to the negative omega L, which is C1 times e to the omega L minus e to the negative omega L equals 0. Now, if we graph this, an exponential function looks like that. So there's no way that e to the omega, there's no way that if omega L is, I don't know, some number, and you look at negative omega L, that's a negative number. There's no way that these things are going to be equal. E to the, let's call this, or e to this number is going to be e to the negative of that number. So that's never going to, in other words, this is never going to be equal to 0. So that tells us right away that C1 has to be 0. So if C1 equals 0 and C2 is it's negative, then we get that C2 equals 0. So here we also get that y of x equals 0. So we get no non-trivial solutions here. Now, I claim that whenever you see boundary value problems, instead of using exponentials, use cinches and coches. And let me just show you why that is. So I'm going to solve the same case, get the same result, but using cinches and coches, and I hope you'll see why it's a little bit easier. So here is that general solution, and let me, instead of writing it with sines and cosines, let me write it with cinches and coches. So I could say that y of x equals, I'm going to use a cosh of omega x plus b times sinh of omega x. I've talked about cinches and coches in previous lectures. They have come up, but I encourage you to review this, especially now that we've recently seen Euler's formula. Let me remind you that so Euler's formula says e to the ix equals cosine of x plus I sine of x. If you just take e to the plain old x, that's cosine of x plus sine of x. And similarly, cosine of x equals e to the ix plus, oh, I said something, no, that's right, yeah. Cosine of x is e to the ix plus e to the negative ix over 2. Cosh of x is e to the plain old x plus e to the negative x over 2. So sinh is very similar. I think I've gone over it before. If not, look it up. You don't need to know too much about these to use them. Okay, so this is y of x. Let's plug in the boundary values. So a great thing about sinh and cosh is at 0, they're just like sine and cosine. So y of 0 is, so just pretend these are sines and cosines. If you plug in 0, you get a times 1 plus 0, so you get a, and that's equal to 0. So that's very nice. This thing went away. And now let's plug in L. So if you plug in L, you get y of L equals b sinh of omega L, and that's equal to 0. And now you should know what sinh and cosh look like. So cosh looks something like, it's like a parabola type thing. So this is cosh of x, and sinh looks something like this. Sinh of x. The key thing here is cosh of 0 is equal to 1, just like cosine, and sinh of 0 is equal to 0. And these things have no other zeros. So if b times sinh of some number is equal to 0, and this number here we know is not 0 because it's positive, that tells us right away that b has to be 0. So we get right away that y of x equals 0. That's what we obtained up here. It was just easier. We didn't have to deal with this system of equations and solving one for the other and this business. So moral of the story is rule of thumb when you're dealing with boundary value problems with functions of x instead of t, use cinches and coshs instead of exponentials. It's time for case 3. I had to clear everything because we ran out of room. So case 3 is when lambda is positive. So let's write that as lambda being, when it's positive, let's say omega squared, which is greater than 0. And if that's the case, then the general solution is y of x equals a cosine of omega x plus b sine of omega x. Now let's plug in these initial conditions. So if we plug in y of 0, so we get a times 1 plus b times 0, so that's a equals 0, and that right away kills off the cosine term. So now let's plug in this next one. So if we plug in y of L, so we can ignore the first term, it goes away, so we get b sine of omega L equals 0. Now what does that tell us? Let's look at the unit circle. Where is sine of x equaling 0? So sine of theta equals 0 if and only if, where? So if theta is, well, it happens there and it happens there. So these are integer multiples of pi radians. So this is 0 pi, 1 pi, 2 pi, 3 pi, etc. So sine is equal to sine of theta equals 0 if theta is n times pi radians. So that means that if we take, so b could be 0, but that just gives us the 0 solution, which we already have, so we want a different solution. So assume b is non-zero, and so if b times sine of this thing equals 0, then that thing has to be equal to n times pi. So we get omega L equals n times pi, so now we know what omega is. Omega equals n pi over L. And so the special case is when L equals pi, we just get omega equals n. So what this tells us is that we have a solution. We have y of x equals b sine of n pi x over L. We get a solution like this for any non-zero n. So n equals 1, 2, 3, etc. Now, we get one for 0 as well, but that's just the 0 solution. So these are the non-trivial solutions. And we get one for negative n's as well, but if we get something for negative n, say negative 2, we can just pull out the negative sign and absorb that with the b. So we get distinct non-trivial, non-zero solutions like this for every positive integer n. Let me say a few words about why this, I think I did this earlier, but so this just says find a solution to this, which is either cinches and coshs or sines and cosines that go through this point and that point. This is different than what I did. So let's look at what these solutions look like. So clearly one of these solutions is just a sine. So this here is sine of pi x over L. But, well, and b can be anything. So any scalar of this, we can scale this as high as we want to or as low as we want to. Will work. But there are other solutions now. For example, what if we look at this function? So this is sine of 2 pi x over L. And that's fine too. As long as it goes through this point and that point, 0 and L, then we're fine. We could also take, let's take a function that, I don't know if I can draw this, like this. So maybe this, let's suppose that one is, 1/3 sine of 3 pi x over L as well. So really, any number of functions like this, or any linear combination of them, is going to work. So if you want to if you look at take a Fourier series built from these type of functions, only the sine waves, that is going to satisfy this as well. And that's why this comes up studying partial differential equations. We will need to solve this, and we will get solutions for every frequency, and then from that we can build more solutions by using Fourier series. Here's example 2. Let's find all solutions to a different boundary value problem. So it's the same ODE, but now instead of specifying the value of the function at 0 and L, we're specifying the rate of change. So these are called von Neumann boundary conditions, and we'll see how they differ. Now the methodology is going to be the same. So we'll look at 3 cases. So case 1 is when lambda equals 0. And so now we have y double prime equals 0 and y of x equals ax plus b. So let's think about what the solution looks like. So before we had looked at for all functions that went through these 2 points at 0 and L. So this is a straight line. Before they had to go through these 2 points. Now it just has to be flat at these 2 points. So any constant function will do the trick. So we know that the solution should just be a constant, but let's verify it algebraically. So let's actually plug in these boundary conditions. So first we need to take the derivative. Y prime of x equals, well, what's y prime of x? That's a. So y prime of 0 is a, which is equal to 0. So we get that a equals 0. Now we also know that y prime of L is also equal to a, and that's equal to 0. So both of these just tell us that a has to be 0. It doesn't say anything about b. So any value of b will work. So y of x equals b. So there is our solution. Okay, case 2. Now again, we could do this using regular exponentials or cinches and coches. Well, let me actually write down what this is. So lambda is, I'm a little bit ahead of you, is positive, so omega squared, which is positive. So now we get y double prime equals omega squared y, and we know that y of x equals a cosh of omega x plus b sinh of omega x. So as I said before, we could use exponentials, except I'm going to do it like this because it's shorter and because you haven't done it as much, and it's good to get used to. So let's take a derivative of this. So the derivative of cosh, this is very nice. The derivative of cosh is sinh and vice versa. So y prime of x is a omega sinh of omega x plus b omega cosh of omega x. So let's plug in 0. Y prime of 0 equals, let's see, so we have 0 plus b omega times cosh of 0, just like cosine is 1. So this is 0, so we get that b equals 0. And now y prime of L, so b is 0. That tells us that this term is 0 and that term is 0. So now we just have the cosh term left. So y prime of L is a omega times sinh of omega L, which is 0, and once again, sinh is this function that is only 0 at 0, so this is non-zero. So sinh is non-zero, and omega is non-zero, and so that means that a has to be 0. So we get that a equals 0, so we get that y of x has to be 0. So as before, we get no non-trivial solutions. Okay, case 3. This is the interesting one. This is when lambda is negative. Oops, let me write that as negative omega squared. And again, we write that because now our ODE is y double prime equals negative omega squared y. And we know that our general solution, y of x, equals a cosine of omega x plus b sine of omega x. Okay. Oh, I said, yeah, that's right. So now let's take derivatives again. So y prime of x equals a omega sine of omega x, and there's a negative sign out in front, and a plus b omega cosine of omega x. Now let's plug in our boundary conditions. So if we do y prime of 0, so now we get 0 plus b omega equals 0, so now that kills off b. So omega is non-zero, so b equals 0. So that will kill off this term and that term, and we are left with just this cosine. So now y prime of L is, so we're plugging L into here, so it's negative a omega sine of omega L equals 0. And remember, with the unit circle, if sine of something equals 0, then that something has to be equal to n pi. So that means that this is equal to n pi. So we get that omega L equals n pi, which means that omega equals n pi over L. And so now our final solution is it's this cosine term. So it is y of x equals a cosine of n pi x over L. Okay, so there we go. And let me call this a sub n because it might refer, because we get a different constant for every n. And then we have this constant term. Maybe I should have called this, instead of b, maybe I should have called this a naught. How about that? Okay, so let's compare what we did here and what we did in the previous slide. So in the previous slide we had, let's see, so we had the y of 0 equals 0, and we had y of L equals 0, and so we had a sine. So any sort of sine wave, not any sort of sine wave, but all of these solutions are sine waves. So these were sine of n pi x over L. Because this first condition, once we said y of 0 equals 0, we know our solution is going to be sines and cosines. But when we specify this, we had killed off all of the cosines. So the a went to 0, and all we got were sines. And then the second condition told us what omega had to be, because it said it has to come all the way back down to here. Okay, so now in this one, it was different. We said at 0, so this is of course L, so we said at 0 and L these things must be flat. So for example, a cosine term, there we go, that is flat at 0 and flat at L. But it could have been cosine of 2, or it could have cycled twice, or it could have cycled 3 times. Any of these cosine waves, these are all cosine of n pi x over L. So here, notice the difference, that we had y prime of 0 equals 0. So that killed off the b. So that killed off the sine terms, or the sinh terms. So in other words, this said, well, whatever the function is that has to be flat at 0, that said we have to have cosines, in contrast to the previous one that said we have to have sines. And once again, the second condition being flat here, we use that to derive what omega had to be. And as before, omega is n pi over L. Here's example 3. Find all solutions to the following boundary value problem. So we're using the same ODE, but now we have a mixture of the conditions that we used in the previous examples. In the left endpoint, we're specifying the value of the function to be 0, and the right endpoint, we're specifying the value of the rate of change. So these are called mixed boundary conditions, because this is a Dirichlet and this is a von Neumann. Some people call them type 1 and type 2. I actually prefer those because they're less arbitrary. Okay, so we finished the last slide with comparing examples 1 and 2, and I want to take that one step further and compare it to this one before we even solve it. So remember that if this is L, so for all of these we have L. The first example we specified, we said y of 0 equals 0, and y of L equals 0. So that's said that we had to have a sine wave, things like, so things like this. So these are all sine of n pi x over L, some scalar. So the next one, we specified not the value, but the rate of change. We said that these things have, so saying y prime of 0 equals 0 and y prime of L equals 0 said that these things had to be flat. So for example, we had things like cosines. So we had cosine of n pi x over L. And maybe something like that as well. Now the third one, let's think about how this is going to differ, how this is going to compare to these two. So now we are specifying, we're saying y of 0, the value at 0, we're saying y of 0 equals 0. So it's going to be like this first one. This is going to kill off the cosine waves. But now we're specifying that the function should be flat at 0. So things like, so something like this. So now what sort of function is going to satisfy that? So, well, it's going to be a sine wave, right? So this might be 2L. Well, there might be other things. There might be, for example, there's another one that if we complete this, you can see where it looks like that. So these are sine waves, but they have different periods. So the period of this most basic sine of pi x over L is going to be 2L, right? Because it would go out to here, 2L. However, the period of this one is going to be, it comes down after 2L, it's going to be 4L. So for these first two, we know that we got that omega was n pi over L, and down here, omega was n pi over L. And let me ask you, what do you think omega here is going to be? So a big question mark. Now it should be off by a factor of 2, but it's always confusing with frequency and period which way it goes. So let's solve it and know that we are expecting something that should look like this. And for your homework, it's a great example. I'm naturally going to give you one where I swap these two. So I'm going to say what happens. Start thinking about it now. What happens if I say y prime of 0 equals 0 and y of L equals 0? So what sort of functions are going to go through here and be flat at here? So things like that. Or things like, oops, that I didn't do that one right. Things like, it's hard to draw these things. Things like that. So hint, they're cosines, but what is their period? Okay, so that's going to be a homework assignment for you. Okay, so case 1 as before. I'm going to go through these quickly because we've done this several times. Lambda is 0, so let's write y double prime equals 0. So we get y of x equals ax plus b. And now let's plug in these conditions. So if y of 0 equals b equals 0, so b is 0, and y prime of L, well, y of x is just the constant a, so y prime of L is a, and that's equal to 0, so we get that y equals 0. We get no non-trivial solutions. Okay, case 2, where lambda is positive. So I'm not going to do this one because we've done it multiple times before, but I'll do this. I'll say y double prime equals omega squared y, subject to these two initial conditions. I'm just going to let you say, I'm going to say exercise. It's good to do this if you haven't done this before. Get that y is equal to 0. So the interesting case is when lambda is negative, so it's negative omega squared, and that's negative. So now we have y double prime is negative omega squared y, and we have y of x is a cosine of omega x plus b sine of omega x. Okay, so now what? So let's do what we did before. Let's plug in 0. We expect that, as in here, that's going to kill off. It's going to kill off the cosine waves. It's going to kill that off. And indeed, y of 0 equals a times 1 plus a plus 0 equals 0. So yes, we get that a equals 0. So we have killed off that cosine term, and we're left with only the sine term. So now y prime of x, so I can ignore the cosine term. I'm just going to take the derivative of that. I'm going to get b omega cosine of omega x. And now y prime of L is b omega times cosine of omega L. And that is equal to 0. Now, where is cosine equal to 0? Remember that sine was equal to 0 at these endpoints, at integer multiples of pi radians. But cosine is the x value. That's equal to 0 right here. Now, what are these? These are half integer multiples of pi. So cosine of theta equals 0 if and only if theta is a half integer multiple of pi. So I'm going to say n plus 1/2 pi. Now it would be wrong to say n over 2, because that would pick up these whole multiples of pi as well. We don't want that. We want only the half integers. So this holds for n equals, I don't want to say equals, let's just say any integer, positive or negative or 0. Okay, so this omega L has to be equal to n plus 1/2 pi. So in other words, we get omega L is n plus 1. I guess I've written that more than I needed to. But now we can definitely say that omega equals n plus 1/2 pi over L. So our final solution is that y of x equals, it's just this sine term. It's b, let's call it bn, sine of n plus 1/2 pi x over L. And that's it. So what was omega again? We said it was off by a factor of 2. The question mark, omega, not like I need to write it again, was n plus 1/2 pi over L. So a little bit different maybe than what we were expecting. So not quite off by a factor of 2, off by 1/2. Okay, so what else do I want to, thinking if there's anything else I want to say about this. So this holds for n positive or negative, but if we get n negative, with like a negative, so here we get sine of 1/2, sine of, so here this is, let's write out what this is. This one here is sine of, in general, it's sine of n plus 1/2 pi x over L, but this fundamental one up here with the longest period, what is that? That's, if n is 1/2, that's sine of 1/2. So let's write this as sine of pi x over 2L. So there's that factor of 2 right there compared to this first one here. When n equals 1, this was sine of pi. This is sine of pi x over L. This one down here is sine of pi x over 2L. So it has period twice as long. Now again, this holds for all integer multiples of n. Let's start with n equals 0 to infinity. We can do negative ones as well, but again, negative signs just pull out of the signs and they absorb in this constant. So we don't actually get anything new if we allow negative signs. Here's our fourth and final example. This one is more complicated than things we've seen before. So we're using the same ODE, but now our boundary conditions are different. Well, our first one is the same, but our second one is a linear combination, y of L plus y prime of L equals 0. So I think this has a name, but I'm just going to call it a more complicated boundary condition. And you can imagine that you can put like a 3 in front of here and a 2 there and do things like that. Or you can have 2 boundary conditions that are complicated like that. But let's just do this one. So first of all, I'm going to leave it as an easy exercise to verify that if lambda is 0, then we have no non-trivial solutions. So y has to be 0. Oops, not y of 0 is 0, but y of x equals 0. And if lambda is positive, so omega squared, which is positive, then we also get no non-trivial solutions. Y has to be 0. So I'll let you check those. It's good practice. But we're interested in case 3. This is the interesting case. When lambda is negative, so let's say negative omega squared, and now we get y double prime equals negative omega squared y. So you know the general solution to this. You know this is y of x equals a cosine of omega x plus b sine of omega x. So the first boundary condition, y of 0 being 0, that's just going to kill off the cosine as before. So this is a times 1 plus 0 equals 0. So a is going to be 0. So that just kills off that. So now we have that y of x is b sine of omega x. So y of L equals b sine of omega L. And y prime of L, well, let's do y prime of x first. So the derivative of this is just, well, of this one is b omega times cosine of omega x. And so y prime of L is b omega cosine of omega L. So now this boundary condition says that we have to add these things together to get 0. I don't really have a good way to interpret what this thing means. Remember before when we drew this picture and we said this is L. I don't have a great way to interpret this graphically. If you have one, let me know. Otherwise, I'm going to assume that it's just a little too general. Okay, so let's solve this. So we have to add these up and get 0. So y of L plus y prime of L equals, I can factor out a b times sine of omega L plus omega cosine of omega L, and that has to be equal to 0. So b could be 0, in which case we get nothing new, so let's ignore that case. So otherwise, this guy is equal to 0. So if that's equal to 0, what does that tell us? So that tells us that omega, see, I'm going to move this to the right-hand side of the equation. So again, I'm just going to divide through by b. And solving for omega, I get omega equals negative sine of omega L over cosine of omega L. So in other words, omega is negative tangent of omega L. Okay. So what does that mean? Well, that means that any omega that satisfies this is going to give us a solution. And so lambda is just the negative of that omega squared. Okay, so what do we do with this? Well, you can think of this as the intersection of two curves. Let me sketch this. So you remember what tangent looks like, the graph that is, right? So tangent looks like, I don't know how well I'm going to do at drawing this. I guess so far so good, but I think I'll do one more. Don't test my luck too much. So I'm going to extend this down here. You'll see why shortly. So this is, I should use a different color. Oh well. This is y equals tangent of XL. Okay, so normally these things would be from negative pi over 2 to pi over 2. So normally this should be pi over 2, and this would be 3 pi over 2, and so forth. However, this is tangent of XL, so we have to put an L on the bottom of this because we're dilating. So this is 2L, and this is going to be L there, and so forth. Okay, so this is the graph of tangent, and now the graph of negative x is going to, let me draw it like this. So this is the graph y equals negative x. And so the omegas that satisfy this are going to be where these things intersect. And so 0 doesn't give us, again, anything new. So I'm going to call this one, so I'm going to call this, I guess now I wish I hadn't drawn these things in here. So I'm going to call this omega 1. I'm going to call this omega 2. And when I say this, I mean the x value of that. That's omega 1. That's omega 2. I'm going to call this, that's going to be omega 3, and so forth. So the omegas are the roots, are, let's say, the positive roots of x minus tangent of xl. And I don't think there's a really good way to do this. I actually did this in advance. I used a computer, and so if L equals pi, then these roots are omega 1 equals 2.029, omega 2 is 4.913, omega 3 is 7.979, etc. So you can find them numerically. This is what they are. And remember, maybe I should have mentioned this earlier, but through all of these slides, lambda, we had to not only find the functions, but figure out what lambda is. Lambda, in all of these cases, are negative omega squared, where the omegas are whatever we found. In this case, it's the roots of these equations. In the previous cases, it was things like n pi over L, or things like that. Okay, that's a good place to stop. Sorry, it's been a long lecture, but we had a lot of stuff to fit in there, and we are just getting started in this section. A lot more things on boundary value problems and Fourier series. Some really cool stuff, so please stay with us.